different tasks. And this is related to the fact that a number of heterogeneous agents try to achieve common goal together. And they should be adaptive, they should be robust, there should be no accidents when we are dealing with this. And the decision making is an important part. There is no central agents that dictate where every agent has to move in this case. So everything has to be distributed as much as possible. So this is the visions that we would like to have whenever we are trying to design such heterogeneous autonomous systems. So this is where our starting point. How can we realize such visions? Now, we've seen a lot of demonstrations in entertainment or even in logistics. The movies that you can see on the left, that is typically the use of drones for showing some kind of a nice 3D animations of a certain figure. The figure on the movies on the left is showing about how we use the mobile robots to transport items in the smart logistics systems. And in this case, mostly the implementations of it is based on the use of a centralized computation server, where the positions of all agents are measured by a beacon, and then they try to compute where every agent has to move in the 3D space, and they just follow the trajectories that has been dictated by centralized computing agents. So in this case, we would like to kind of depart from centralized solutions. We try to see whether we can implement a distributed one. But when we take a look into the distributed solutions, we can try to learn what is actually the behavior that we expect when everything is distributed. So the movies on the right, this is one of the famous results or research done in traffic systems, where they try to experiment how humans behave in the real traffic systems. And when we consider human as a real intelligence being, you can see that there is a bit of problem here. So everyone takes their own decisions. Everyone has to drive 30 kilometers per hour. They have to maintain a certain spacing. So you can imagine in the highway, you have to maintain a certain spacing with the neighbors. So you could expect that everyone is clever. They have to maintain a certain spacing, 30 kilometers per hour. How difficult would it be? So now let's try to take a look how it is in reality. So everything tries to drive 30 kilometers per hour. But because everything is distributed, when there is something inconsistency in the behavior of some of the agents, you can see that some of the traffic jam started to occur. And that is precisely what happens in the real highway. Whenever we try to drive from Bandung to Jakarta, you will see that traffic jam happens in some of the area, even though there is no narrowing of the channel. You can see that sometimes it's not moving smoothly. This is due to the fact that the behavior or the dynamics that is induced here can indeed induce such traffic jam. Of course, we've seen a lot of nice movies in the internet. One of them is like this one. It's drones lifting a container, or even in this case, scientists have tried to showcase that they are able to design an algorithms such that many, or I would say thousands of small mobile robots is able to form a very nice formation. So in this case, it will show a pattern of a famous university in Europe, and that is, I would try to wait a bit, and that is the EPFL. So that is one of the famous university in Switzerland. But both of them are actually misleading videos. I wouldn't say fake, but it's just misleading. The left movies is indeed a fake movie because it is based on the visual effect. And why do they do that? Because Scania would like to put a marketing video, picture themselves as one of the innovative companies for transportation, but all of them is just basically computer generated movies. While on the right hand side, what has been done by the EPFL is that they are starting from the real logo, and they program all of the robots to move randomly with collision avoidance, of course, move randomly around the room. They record everything, and then what they do is just to play back from the end to the beginning. So when they do that, it created sensations that all of the mobile agents started from a random positions, and then they converge to the right logo, seemingly that they are able to do that in a distributed way. So in that case, both are kind of a misleading. They wanted to showcase that they are innovative, but for most people, when you are not in the field, you would think, this problem has been solved. So we should try to aim for further goals. So since this has been solved, well, maybe we can try to solve much even difficult problem. But in fact, some of the case is still quite challenging to solve. And that is basically what I would like to convey in this message. Whenever you see something fantastic, be a bit skeptical, and then maybe you could try to test yourself whether you can understand what is the mechanisms behind it. So I would like to start with a formation skipping as a basic building block in creating a collaborative agents. And then I would move into the group motions, where now instead of moving one individual agent, we try to move the whole agents as an entity to perform various different tasks. So in this case, a group of agents will move from one area to another area, and then they also have to perform collision avoidance collaboratively. Again, I would like to focus in the implementations of distributed solutions. So I would like to try to avoid as much as I could in using centralized solutions. And then I would like to see on the collaborative simultaneous localization mapping, formations in task space, and some few topic. And I would like to see the timing as well, whether I can cover all of those things in time. And maybe I would like to ask the moderator, how long do I have? Is it 2 hours or 3? I'm kidding. How many hours?
Yeah, we have 2 hours.
No, but for my presentations?
So yeah, 1:30.
All right. So let's see if I could deliver such a full course of full lecture for this one. I will try to aim for about 45 minutes. Yeah. So, but still, if you have any questions, just raise your hands and I want to address your questions. So let's start basic formations control. We, as a prototype, I would like to keep using this 4 yellow robot, and we assume that everything is just using omnivores. They can move in the X and Y directions easily without any problem. There is no non-autonomic constraint in this case, and we assume that every agent can only measure locally, meaning that there are sensors that can measure their neighbors. And the way they measure their neighbors is represented here by spring-like symbols. So in this case, this robot is able to measure this robot is able to measure this robot, and vice versa, and the same with the others. And these measurements can be anything. It could be distance measurements, it can be bearing measurements, it can be relative positions measurements. So relative positions meaning it is just the difference in the X and Y directions of the other agents with respect to a certain agent. So that is called the relative positions. Now, in most cases in the formations control problem, we typically start from a simple problem formulation. So the simple problem formulations, in this case, the simplest one, is that every agent uses the same type of informations. So if one agent is using distance measurements, and then that means the other agent is also using distance measurements. So that's the typical setup. The use of heterogeneous sensor systems poses additional challenges, and that will be covered at the last part of today's lecture. And that is not a trivial problem. So if everything's just using distance, we have a nice elegant solutions. But if one agent is using distance, the other one, this one is only using bearing. So then when they measure each other, this one is measuring distance to this one is measuring bearing to that one. There should be a bit of like a compatibility in the way we define the formations, and that created a bit of a issue sometimes, but I'm not going to cover it today. I will try to just give you some of the problem that might be encountered. The assumptions for simplicity again, so we start very simple. Every agent is assumed as a simple integrator. So they can move in the X and Y independently, and their dynamics is just an integrator. So meaning that the movement is just represented by a velocity, and we are able to realize such a velocity in the X and the Y directions. We could deal with the realistic situations where the dynamics of this is described by second-order systems, but for simplicity of today's lecture, I will just focus on using single integrator. Now, to make it a bit more clear to most of you, I'm going to start introducing some math notations. And if you cannot follow what I'm presenting, just ask me immediately. The way we represent the measurements, we use graph theory, and the graph is represented by the symbol line G, and this line G is represented by two elements. The first one is the set of vertices, and the second one is the set of edges. So in this case, the set of vertices are 4, and the set of edges are also 4. So there are 4 edges as well as 4 vertices. And the formation shape can be described by the way the link or the edges is being defined. So the edges is representing the pair of agents that are connected by an arrow, and this arrow is representing, again, the way the information is being used to define the formations. I use an arrow just to simplify the formulations, although in the reality, the measurements is taken both ways. So just to avoid any miscommunications, this arrow does not mean that this agent is only measuring this one, but this one is not measuring this one. That's not my purpose here. So my purpose here, every time there is an edge, we agree, let's agree with each other. Every time that there is an arrow, it's just a both ways measurement. So if there's an arrow here, it is meaning that this agent is measuring this one, but also that this agent is measuring this one. And we use arrow here just to be able to define the incidence matrix in an easy way. So now, with this arrow agreement, consensus on the way we use the arrow, then we can define the incidence matrix, which is describing how the vertices is being mapped to the edges. So B is a matrix that relates to the number of vertices to the number of edges. And each element is represented by +1 or -1 of 0. It is going to be +1 when the ith element in the kth row is belonging to the tail. So if it belongs to the tail, that is going to be +1. If it is belonging to the head, it will be -1. So with these notations, we can take a look at that example. In this example, we have 1, 2, 3, 4. That is the number of vertices. The edges is defined by 1, 2. So that is the way we put it. 1 into 2, 1 into 4, so 1 into 4. So this is really following the way we indicate the arrow. 2 to 3 and 3 to 4. And when we take a look at the incidence matrix, then we just take a look into the first column. When we take a look into the first column, 1, 2, so that is about the first edge. So 1, 2, it's the ith row is 1 because it is in the tail, and it is -1 because it is here, because this is at the head. Yeah. So and we follow that the same for the second column, the third column, and the fourth. So now, based on the use of incidence matrix, we can define relative positions. So Z1, Z2, Z3, and Z4. Since now we are going to assign for the graph positions. So for every vertices, we will assign a physical variable there, and the physical variable is just positions. So positions 1, positions 2, position 3, and positions 4. We denote it by P. And typically in the formations, we call the pair of line G and P as a framework. So this is how we can define the formations. So G is just representing the way information is being exchanged, and P is representing the physical variable that we use. The relative positions is just the difference between the Pi and Pj for the edge I and j at the kth edge. So that means at the first edge, which is Z1, and that means it is P1 minus P2, because the first edge is between I and j. So this is P1 minus P2. And in that case, the way we can write it down in a compact way is by using the incidence matrix as we used before, multiply by the Kronecker product of identity with dimensions of 2. Why we use Kronecker product of identity of 2? Because P defines in the two directions, in the x and in the y. So the Kronecker product is just basically copying the way the incidence matrix is being used in the x directions as well as in the y directions. Yeah.
Okay. Good morning, Professor Bayu.
Yes.
Yes. My name is Anugrah from Yogyakarta, and I'd like to ask you about the P1. I see that. Oh, sorry. All of the edges are not. They don't use. They don't make a loop. I think because the P1 there are two edges flowing out from the P1.
Yes.
Does it mean something?
Yeah. So in a P1 there are two arrows. That's what you meant, right? So
Yes,
P1
that's right.
to P2 and P1 to P4. And that is also can be seen in the set of edges. So in the set of edges, you have 1 to 2 and 1 to 4. And this is kind of representing that agent 1 is measuring agent 2, and agent 1 is also measuring agent 4. And the same as agent 4 is measuring agent 1, and agent 2 is measuring agent 1, and agent 4 measures agent 1.
So the edges, each edge represent who measure who.
Yes.
Okay.
Yes.
Thank you, Professor.
Okay, so I will continue again. So everything can be represented in a compact way by using the incidence matrix multiplied by a Kronecker product of identity 2. And I said earlier, it's just copying how the relative measurement is being used in the x direction as well as in the y directions. I think you need to click on my slide because, yes. Using the relative positions, then now we can define the quantity that we can use to define formations. Previously, we only defined about relative positions and positions. But now, in order to define formations or shape based on the information that we have, we can define edge functions. So in this case, I would call it distance-based edge functions. Why it is edge function? Because the functions is defined based on the edge information. So in this case, the edge information is the relative positions, Z1, Z2, Z3, and Z4. And when I call it distance-based, because the way we define shape is using the informations of the edges, and in this case, we are only using the information about the norm of the relative positions. So if you remember, the relative positions is about the difference of positions in x and y directions of every agent. And when you compute the norm, and this is Euclidean norm, and I would recall Euclidean norm is just like using Pythagoras theorems to indicate the distance between the 2 points. And you can see here that I am concatenating, I'm collecting all of the informations about the distances of all of the edges. So in this particular example, we have 4. So you can see it on the left, that is how we define the distance-based edge. And based on the edge functions, then we can define the desired shape. So this desired shape is basically, you set a particular prototype of the desired formation that you would like to have. So in particular, if you like to have formations of a square with a relative distance of 1, then you can set, okay, this is my prototype of the shape that we would like to realize. And they have to maintain a distance of 1 of each other, and it will create a square. Then that we can call it as our prototype of a shape, and we can define the shape, or all of the shape that we can define using edge functions is basically all of the positions defined by the set. Calligraphic D is defined by all of the positions in the 2D space. You can imagine 2D space from minus infinity to infinity, from minus infinity to infinity in both directions. So all of the positions where the edge functions evaluated at those positions is actually the same as the edge functions defined in the prototype positions. So that means if this is our prototype, then if I define this is another space, I could define another shape of a square, even though it is rotated, but as long as they have the same distance of 1, that belongs to this set. You could also define another place with a different orientations that is also belonging to the shape that is admissible in our formations. So you can imagine that this set is actually in infinite size of the set. Yeah? But it may have other shapes than our intended desired shape. If we only define, so the way we define the edge is very important. So in this case, we wanted to define a square. So you define 1, 1, 1, 1, using this only 4 of the edges. But this one can also satisfy the same constraint. So in this case, you can imagine it is 1, 1, 1, and 1, but it is no longer a square. So in the formations literature, the way we define the link before, is only using 4, is creating a bit of problem because that would not lead to the shape that we would like to have. And this is actually, we call it as a non-rigid formations. We can make it a rigid by having an extra measurement. So you can have this additional edge, or you can define another diagonal one. And in that case, we can create it what is so-called infinitesimally rigid formations. Now, how to define that in a rigorous way? We can take a look directly, actually, we can characterize it by looking into the edge functions. So if you define your edge functions like what I defined before, and then when you calculate the Jacobian of that, with respect to the positions, and when you calculate the rank, if the rank is equal to 2 times the number of edges minus 3, then it is infinitesimally rigid. So you can forget and okay, so what I could say as well is that it is invariant under translations and formations. What does it mean? Meaning, if I go back to the previous one, this is infinitesimally rigid formations, and this is invariant under rotations and translations, meaning if I rotate it, if I move it to the right hand side, or if I move it to the above, those are still satisfying the same constraint, and those are still defining a square. You can imagine it directly, right? The same goes for a 3D shape. In a 3D shape, you can just calculate the Jacobian of this, you calculate the rank, if it is satisfying these conditions. It is also infinitesimally rigid in the 3D space, and it is invariant under translations and rotations in the 3D space. So some of the counterexample. This is, as we have seen, that this is not an infinitesimally rigid because it can create a parallelogram. This is also not an infinitesimally rigid because you can move the inner part, like using rotations, satisfying the same distance constraint. This is also not, because you can, this part you can rotate it a bit, it is still satisfying the same constraint. this is rigid in the 2D space. In a 3D space, this is not rigid, this is rigid when you are making like a prism. So now, once we have defined what do we mean by rigid formation, so we know how the shape look like and what would be the admissible shape according to the way we define the edges, then the challenge now is how can we design a controller if your dynamics is defined like this one, a simple one, as the simplest one as I have mentioned before, is a single integrator. The velocity or the time derivative of the positions is equal to your control. And we would like to design this control input in such a way when you are starting from incorrect shape, you would like to converge to the correct shape. And the correct shape is the one that we have defined before. So this one is the correct shape, and we wanted to design a control input in such a way that when they start from a wrong shape, meaning that they are not belonging to this set, they can converge to any positions of this set which is satisfying these conditions. Yeah. So that's the problem. The problem is how can we design control input here such that when you evaluate the edge functions based on the current positions, you would like to realize that it should go to the right prototype shape as the time goes to infinity. Or in other words, when you take a look into the distances at every edges, so the distance at the above edge, the side edge, the bottom edge, as well as the diagonal edge, they should go to the right distances as the time goes to infinity. Any questions so far? I think it's kind of a simple problem formulations. Now comes one of the elegant results in the literature. You can actually create a simple controller based on what is so-called gradient-based distributed controller. And that gradient-based is basically you define potential functions based on your available measurements, so in this case, the relative positions. And then if you define the potential functions properly, when you design a gradient-based control, so this is gradient-based based on each of the positions, then the controller or this controller will guarantee that the potential functions will go to the minimum of the potential functions. What does it mean? So if your potential functions is defined at every edge, and at every edge you try to make sure that that potential functions has the minimum at the right distances, and when the distance is not correct, it is kind of a positive. It will make sure that this controller will guarantee that your systems will converge to the bottom part of your potential functions. So the theorem that we have in the literature, and this is also one of the review paper that I would recommend, if every of the potential functions is, let's say, continuous or real analytics, then the gradient-based solve this controller solve the distributed, I would say, the distributed formations control locally, which means that it will converge asymptotically to the desired shape. So this is kind of a very nice result. For that, let's take a look into how it would look like for a particular gradient or particular potential functions. One of the simplest potential functions is like this one. L can be any number. You can take it 2. If you take it L equal to 2, that is the standard Euclidean distance, or Pythagoras law, if you like to imagine it. So if you put 2, then it is just a distance square, the current distance square minus the desired distance square for that particular, for each individual edge, and then you put square and 1 divided by 2 times L. In this case, L is 2, so 1 divided by 4. And you can imagine in your mind that this one, if your current distance is higher than the desired distance, then these functions will grow. So if this zk is further and further away from the desired distance, this number will grow even higher. And when this is less than the desired distance, it will still growing again. So it has a minimum at the desired distance. And now when we take a look into the gradient of this one, it's very simple. So if you can calculate the gradient with respect to one of the agents at this particular edge, and that is actually given by this one, which is the relative positions multiplied by relative positions norm to the power of this. So when L equal to 2, 2 minus 2 is 0, so this is gone. And then you have 2 and 2 here. So this is kind of a simple, you would like to see what is this actually. Remember that Zk is Pi minus Pj, and when you calculate the gradient of Pi minus Pj with respect to Pi, then it's just 1, because you take the gradient with respect to Pi. And that means that this one, if Pi is just equal to this one with a plus in front of it, but it will become minus if it is taking the gradient with respect to the other edge, which is the minus part in the Zi in the Pi minus Pj. So it is either plus or minus of this one. A simple one, I will take L equal to 1. So when I take L equal to 1, then this is basically the control law for every edge. This one is indicating directions. So when you see this, this is relative positions divided by the distance at that particular time, and this is giving you a unit vector. So this is really just giving you a directions. And this one is giving you the distance error, and it is plus 1 if I is at the tail of the edge of K. Otherwise, if I at the head of the edge K, then it will be minus 1. How to imagine that? I would like to use this graph. This is rigid formations. Then the distributed formations control basically is given in the following sentences. The velocity of every vehicle, in this one for every agent, is just sum of all the directions to the neighbors multiplied by the distance error to the neighbor over all the neighboring agents. So this means, I just use these illustrations. This is not the correct shape, because I would like to go to the square. So in this case, this agent will have directions to the neighbors. So there are 3 neighbors here, and it has different distance error. So this one has a certain distance error. In this direction, it has a certain distance error. In this direction, it has a certain distance error. So when you add them together, also the other agents will do the same. This one will go to that direction, go to this direction, and goes to that direction. They are not going to this direction because this one, let's just assume that this one has already the right distance. So if it has already the right distance, then there is no contributions in this direction. So all the contributions is only in the directions where the error is not yet 0. So that's how you can interpret it. And by implementing that one, you will guarantee that everything converges to the right shape. But now, what happens if the distributed control law does not measure the same distance? So for instance, I will tell you what the problem would be. So when they are not using the same distance informations, what would happen, and this is also the problem that has been presented in 2012, 10 years ago, that the formations will converge to undesired group motions. It is actually a circular one or helical motions in a 2D space. So they are converging to wrong formations, but it's not only converging to the wrong formation shape, the whole group will move in a circular way. You will see in a movie that I will show you shortly. So in this case, the 2 pairing agents at the edge K, so the agent I in the edge K, also the agent J at the edge K, they are not using the same distance. Why it is possible that this happened? That could happen because there might be some offset error in the sensors. So if I measure to the moderator with my own eye, I might measure now is about 2.5 meters, but the other agents might measure different things because of the bias that is present in the sensor systems, for instance. So in that case, then they may not be implementing the same distance, desired distance informations. So if we take a look into the previous example of two pairing agents, so one is plus and one is minus, the problem lies that in these numbers, they may implementing different numbers. So if they are implementing different numbers here, problem will occur. So what we have done to solve that problem is actually introducing an estimator, and this is borrowing an idea from observer design. So we try to include a corrections term here, where for the J agent, the discrepancy in the measurements is abstracted by having this mu k. So this mu k is representing differences in the distance informations, and we would like to try to cancel this mu k. And the way we try to cancel this mu k is by introducing an estimator. And the estimator is not only canceling the mu k that is only a constant bias, it could also be something that has this form containing sinusoidal signal. You might think, okay, so constant is like what I've mentioned earlier, that there is a bias in our sensors. One is measuring 2.5 meters and the other one is using 2.6 meters. But there could be another noise in the sensor that created this harmonic noise. That could, for instance, coming from the frequency of the power grid if you're using an AC electrical source, or this could also be representing wave on the oceans at certain frequencies. So one agent is moving up and down with a certain frequencies at the oceans, and that's kind of representing these changes in the measurements due to the periodic dynamics from the environment. So in this case, then, because we would like to cancel the discrepancy, we introduce this estimator, and we hope with having the right estimator that would cancel the mu k that is being given here. So that's the idea. So you have something that is actually kind of like an error or disturbance, and by having the estimator, this one will cancel the mu k that is shown before. And for that one, what we need to do is that for every pair of edge, there is one agent that is something that we assign as an estimating agent, and that agent is the one that is trying to cancel the bad mu k as has been shown in the previous slides. And how mu k is being generated, it is generated by this simple, not simple, I'd say it's simple, but maybe it's not simple to most of you. Mu k is being generated by dynamical controller, and in this dynamical controller, you have a kind of a memory which is trying to match with the frequency or the amplitude informations and the phase informations from the disturbance. And that is the role of this memory state. And it is always being corrected by the error that we obtain from the current error measurements minus the estimator. So we have the corrections here, and when the error is becoming 0, there will be no more update into this mu k. So the mu k is already able to copy the disturbance signal. And this is how mu k is being generated. This is just basically a mapping from the memory state to the disturbance coming from the environment. What is lambda? Lambda is basically a matrix generating a constant bias informations, and that is basically this upper left, that is just an integrator. And you have an element here which is a skew symmetric, and this is actually generating the sine wave. So that is a model of oscillator And this is responsible in actually trying to approximate this part, the harmonics information. So the harmonics is basically just representing by an oscillator. That's why we add an oscillator in this dynamic controller here. So in short, the controller with a distributed estimator is given by the following. This part is similar to the formations controller as before. You have an additional element, which is the corrections part, and this is the state estimator or the disturbance estimator. And we have a certain theorem. I would not spell it out what this the theorem is, but basically what we have here, we have a conditions under which we can guarantee that everything converges to the right shape and they are no longer moving in the unwanted motions. So the conditions is based on the edge functions and based on some informations on the current relative measurement. So if everything is okay, then the theorem says that there exists a maximum gain such that if you pick the gain small enough, so this is the gain in your state equations, in your dynamic controller, if you choose the gain small enough, then you can guarantee that your system converges to the right shape. So a bit of a summary. The distributed formations control, whenever there are some discrepancies or error or noise, then basically you have the same as before, the direction to the ith neighbor multiplied by the distance error to the ith neighbor plus a correction term. So that is something that you have seen here. So this is the coming from the previous formations control, and then there is a corrections term here. Yeah. And the local estimator state is basically the previous estimator state plus the term that depends on the error to the neighbors. And that is actually what you can see here. The current state is equal to the previous state plus some corrections term. Yeah. You can find it in the paper in 2015. It's already 7 years ago. But I like to show movies. So I'm going to show movies on the left. That is what happens when these agents has, so the red one, they have a discrepancy in the measurements. And I would like them to converge to the square. But you can see that they are now converging to parallelogram, which is the wrong shape. And not only that they converge to the wrong shape, they are going to move in a circular way. The same happens on the right. So the left one is using a small epox robot that we have. The right one is using the Nexus robot, and it is really using the local measurements using LiDAR. And in the LiDAR measurements, we have a small discrepancy of about 1 millimeter in some of the agents, and even 1 millimeter discrepancy that can introduces unwanted behavior. So on the left, you see that there is unwanted behavior and it's moving constantly. Although the person is trying to move around, they still converge to, firstly to the square, and then after that to the parallelogram. On the right, you can see that when we speed it up by 14 times, everything is drifting away. So this is not the right behavior that we like to have when we try to implementing it in the real world. So by using our estimator, you can see here now that they are able to form the right formations. The estimator is able to converge to the right correction term. And what good is that when we speed it up these experiments by 14 times, you can see also this student of ours still working on the table there very seriously. You can see how he's head banging. This one is still really robustly maintaining its formations. Why it is important that we like to have a stationary and they are not moving not according to what we wishes, and they are not converging to the incorrect way, because when they are going to bring let's say an airplane wing, a very large one, you would like to bring this using 4 robots. If they are converging to the wrong shape, then it might fall down because the center of the mass has changed, because they are not in the right formations, And then the expensive aircraft wing can fall down, and that's really an expensive experiment. And that's one of the things why we try to make sure that we are able to make a formation. And this is just showing that they can move as a whole group. The mechanism to do that I will show you shortly. Any questions on the other formations?
I need some information about the noise. What do you mean by noise?
No? Noise. Yeah, noise meaning,
Not meaning of noise, but what is noise in this case?
oh, so in this case,
Yeah.
it's the measurement noise. So they measure not the same way. Because every agent is measuring in both ways, and they are not communicating the information. So when we take a look, when we look into the example on the right, they are using LiDAR. And when they are using, each is using LiDAR, the LiDAR is measuring the distance with the neighbors, and that distance informations, they may not be the same between one another because of the calibrations problem. So when they are not calibrated properly, one may have a slight difference with the other. LiDAR, even though it is just 1 millimeter, it can already introduce a bit of problem. That's what I meant by noise. Yeah. Okay, now we try. Yes.
The measurement didn't use the direction.
The measurements we do directions. Use directions.
So it's not just the distance.
No, it's not distance, but also directions. But in this case, that's a good question that I haven't addressed properly just now. So in the controller, let me try to, yes. When we are implementing this controller or even the previous one, the good thing about this algorithms is it is agnostic to the frame of coordinate. So if one robot is using frame of coordinate north and west, the other agent is using east and south, so they are not using the same coordinate systems. But since they are only using based on their local measurements, so they measure according to their frame of reference directions to the ith neighbor, it is independent on the global frame of reference. So they are not using the same north in all agents. So in that case, indeed, to address your questions, they are still using directions and also distance, but not in the global frame of reference.
Back to this noise, sorry for asking.
Yeah.
Is this a kind of a random noise or?
No.
This is only
So that is a noise that can be generated by this generator. So the noise that we represent is actually this is the limited noise that we are considering.
Because I saw the pictures, it looks like you are not.
No, so in the movies there are some noises, a real noise that one. So we are not dealing with those noise.
Okay. You don't take it for granted.
No, because those noise has a zero mean values, so it's just.
Although it looks like a bit heavy, yeah?
Although it is a bit heavy, but they still have zero mean. Well, when there is a constant bias, then it's no longer zero mean. But because we try to cancel that constant offset, then it's becoming zero mean. Okay, so I will move on to the next one. The next one is about the, I forgot, the next one is, oh yeah, this is about group motions. So previously we see only the way we deal with external disturbance acting to the systems from the sensor. We try to look into different problems now. So we would like to know if we are able to achieve the robust formations. Now, how can we achieve a different task? Meaning, we would like to bring the aircraft wing from hangar to another hangar for maintenance. for instance. So one easy way to do that is just assign one of the robot as a leader. I would assign this top right as a leader. When you move it, it will create an error of the distance in this case. The other agent try to correct it, but again, since the leader is always moving, the other try to follow up, but the steady state motions is actually a number of edges is constantly not in the right formation, so the shape is actually deformed. So it's not longer, in this particular case, they are no longer square, but it is a bit deformed. So of course you could design a different things for every robot in order to avoid this case, but I'm not going to go into that solutions. If we are looking into the rotations, you can think of the same problem solutions or problem formulations. When this leader tries to rotate, everyone tries to follow, but at the end of the day, it's still creating a bit of deformations in the formation shape. So how do we handle that? The way we handle that is actually we exploit the fact, because we know before when there is a distance error, everything can go to wrong formations and then they can do rotations or they can do translations. And actually we can use those to our benefit. So what we do is actually we implement the standard formations control, but the smart thing that we can introduce is that the distance error is not only a functions of the desired distance, but it can be a functions of the desired group motions. So we intentionally create the bias. So previously when we have a bias, everything goes wrong. But what we try to generate here is we introduce the bias ourselves. Why we introduce bias? Because we like that the whole group is moving. But we have to introduce bias in a smart way, because we wanted to make sure that even though the whole agents move, we do not want them to have a deformed shape. So the shape is still the correct shape, but then they are moving in the right directions. That's how we can control the whole formations. So that is presented in the paper 6 years ago. And the real implementation is quite simple. So basically, you started with the right formations, but then when you wanted everyone to move in a certain way, you compute the right bias. That's just computing one time. And then you send that bias to all agents. So that's also one type of one-time information sent out to all agents. And then after that, you do not do anything else, the central computer. So indeed, there is kind of a centralized computations, but then it's just like an orchestrator. So it's like a conductor. So there's a conductor, the conductor says one value, everyone's just following, and then they are still achieving the right formations. So in fact, in the simulation, or not in the simulation, in the experiments, you have seen how the whole group is able to move one way to another, and that is using our algorithms. But the nice, interesting part is on the right-hand side. In the right-hand movies, we're implementing it to quadcopters, and in these quadcopters, they try to bring a heavy object, and this heavy object cannot be lifted only by one drone. So what happens here is that they are forming formations like what we have done before, and they are able to maintain robust formations, and then they are able to lift the object collaboratively. And now, not only they are able to lift the object, they can move to one direction or another. And of course, as you can see here, sometimes there are issues with the air motions, but they are able to correct those properly. You see that before it's starting from the small area and then to the big area. That's also part of the motion that we can introduce. So the motions we can introduce rotations, translation, but also scaling. So you can scale it big, scale it down. Another problem that we try to investigate. So not only formations, not only motions, but also distributed obstacle in a group way. So we would like to do that in a cooperative way. How do we do that? So when we take a look into the picture on the left, we assume that we are able to do formations, motions properly. But now you can imagine that one of the agents is able to detect an obstacle. So in this case, the robot on the top right is able to detect the obstacle, but the other agent does not know about it. So the other agent does not know the presence of an obstacle in the room. What happens is that the agents on the top right try to evade this obstacle. As a result, the whole group will be deformed. So they are no longer having the right formations, and that is something that we would like to minimize as much as possible. So how do we rectify this problem? One solution that we have come up in a paper in CDC in 2019, 3 years ago, is actually we still use the old or the previous formations and motions, which is the first part, but then we added a local distributed obstacle avoidance estimator. So this local obstacle avoidance is basically every agent has its own local collisions avoidance, but then they communicate with the others about what is actually the state of their collisions avoidance estimator. And the way we design it is based on the repulsion control law plus what is the neighbors gives you the information about their own state estimator of the collisions avoidance. So they only communicate about their obstacle avoidance estimator, but they are not communicating about their sensors. So they are not communicating their sensors at all. It's only about the state. So in this case, you can see on the simulations on the left, we start from the desired shape here, and then when we wanted these agents, the group, to move to the origin at a 0, 0, it faces two obstacles, the first one and the second one. And you can see here that this agent, the agent on the bottom right, started to enter. So the blue one is actually margin of safe, the safe margin. So it is allowed to move to the blue one, but it must not goes into the red one. So it goes to the area where it should try to evade. And what happens, the other agents, since they are implementing local estimator of collisions avoidance and they keep constantly communicating the informations with each other, these agents also do a similar collisions avoidance. The same with this agent or the light blue as well. When we take a look into the distance informations, you can see that the three agents, the blue one is able to maintain the right distance at all time, and the second edge, sometimes it is dipping, so that means the distance in that particular edge changes, but it only changes very slightly. Also the other one. So this is kind of showing that the distributed local collisions avoidance works, that it can minimize the possibility of having a complete disaster of trying to avoid a local obstacle. Any questions so far? This is becoming a long
Very
seminar.
interesting.
I will try to go very fast. Any questions? No? This is one of the difficult problems that we have encountered. Yes.
About the previous one, so in here you also implement the bias system, not yet.
Yes. You mean bias to do the motions, right?
Yeah, because here actually there is no leader, right?
No leader.
But you know whenever the one agent facing an obstacle
Yes.
and try to change some direction,
Yeah.
so the other agent should know about that.
Yes. But
So,
the idea,
so that information is come from what? From the movement.
It comes from the local estimator.
local estimator, meaning that the other agents, he doesn't know whether the other agent has the obstacles, right? Because
No,
there's
no,
information.
no. Right. So that means if we can imagine that this is 1 million agents, so in this case it's 3. So 3 is, we can imagine that all information is being exchanged to this one, and information about local estimator is being exchanged to this one. But when we take a look into 1 million agents, and it's only this one that's detecting that one, that information of our local collisions avoidance information is being distributed to the whole rest of the network.
So there is
Because
a
of the-
communication about the obstacles, the position of the obstacles.
They are not communicating the position of the obstacles because everyone can use a different frame of references. But they are only communicating that this agent is starting to execute collision avoidance.
Yes. So other agent just following because he
Yes.
just
But they are a bit reactive because it's not only observing, but also because it has a prior information. Oh, so I have to move to a certain directions. Otherwise, it has to observe where it is moving, or it's moving to these directions. So I will move to these directions.
so
And-
it kind of like that agent becomes the leader. Right?
No, not in that case. Yeah, if it is only about the leader things, then the other agents cannot preemptively do the right actions. By preemptively meaning it does not know where to go first because it has to see where the agents or the leader is moving. But because they are communicating these local collisions avoidance estimator, then the other agents in real time they already kind of know where they have to move.
So the other agents knowing that there is an obstacle from the other agents coming from the algorithm
Yes.
obstacle estimator.
Yes. Yes. So they are not communicating the locations of this one. Only about communicating what is actually my actions would be. Like that. And the other agents try to mimic, okay, so he tells me he's going to go to these directions. I will try to. So in some sense, it looks like a leader-follower configurations. But
it is not.
yeah,
Because-
you
because
can
it-
say it in that way.
Because it is coming from the estimator.
From estimate. Yes. Oh, yeah. Go ahead. Okay, Anugrah, you can ask.
Oh yeah, Professor, I'm sorry.
Oh.
Related to this figure about the left figure. So I saw that the obstacle is represented by two circles, red circles inside circles and the blue ones. What does it mean? Because I saw that one agent crossing enter the blue area. Is it looks like some area around the obstacle?
Right.
So the
So
obstacle is the red one.
yeah, the real obstacle is the red one, and the blue one is the area where the agent has to activate the collisions avoidance.
Oh, okay. So
Blue one
I
is
understand. Yeah,
blue
yeah.
one is still a safe region, but then that is the area where the agent has to really execute the
Oh, okay.
maneuver. Otherwise,
Okay.
it will hit the red one.
Yeah, understand. Thank you,
And,
Professor.
and in that case, we are not only concerning about the circle motions, but we could also circle obstacle, but we could consider an arbitrary shape. So it's not only circle. This is just for a simplicity.
And then one more question, Professor. This obstacle is static obstacle.
Yes. In this case, it's
Okay.
that.
So you don't consider about their motion in this paper?
No,
Oh, okay. Yeah, thank you.
and I would be happy to consider the moving obstacles as well.
Yeah, that's right.
Right. Can you click on the? Yes. All right. So I'm going to go to one of the difficult problem that we have faced last year or 2 years ago, and that is actually formations, but not using a single integrator. Well, depending on what we mean by single integrator. So in this case, we are trying to make a formations, but on the manipulator arms. So you have the manipulator arms, and the one that we would like to solve is actually the formations of the end effectors. So not the positions of the base, but the positions of the end effector of the manipulator arms. So we don't care about the base. Well, we might care about the base, and let's assume that the base, you already have formations control for the base itself. So if it is talking about mobile manipulators, the manipulators are being brought around by mobile robot, and we already implementing formations control for the base. But now we would like to do formations control of the end effector. The difficult part of the end effector is because we have to realize the formations by controlling the joint. And how can we actually map the control that should be implemented or at the end effector to the joint space? So the solution that we have come up is that we try to compute the actual velocity at the end effector, and then at the joint forces, because it's pretty much complicated, so it's not just a simple inverse kinematics. We performed a really complicated formula, so I just put it functional operator of the local joint displacement. So this paper is available in, it's not, so there is a paper that we have submitted to IEEE Tech. If you are interested, you can take a look at my website, and it is still in archive. So we try to achieve like this one. So you see that there is an, so the base is being fixed, but you can see that the end effector try to achieve a certain formations. And I'm sorry that we have quite a bad robot. It's moving always is kind of flexible, but we managed to achieve what we wanted to. The other one, vision-based. So previously we talked about distance-based, and now I'm trying to think, okay, distance-based is using LiDAR. Can we use other sensors, using camera, for instance? And if you try to think about using camera, what sort of information that we can use from the camera to do formations control? And I assume that from the camera, it's a bit difficult to do the distance measurements. And something that we would like to do is maybe we can see other features in the image plane or in the image itself, and whether there are some features that we can use to do the formations. So something that we have come up is actually pretty much simple. If we assume that every agent can be represented by circles, what we can try to observe is that, for instance, this is so when you take a look into the figure on the left, you have two agents, agent I and agent J. Agent I measures agent J using camera, and if you imagine that if it is using camera, what does it see? It sees an image, and it can see the outer edge of the robot. And the outer edge of the robot is basically the outer element that you can see from the circle, and that is actually something that is forming perpendicular directions to the radius. And that means if you just observe the leftmost and the rightmost of your neighbors, you can have a relation of the angle or inner angle to the neighbors, and you can in fact use inner angle to define your formations. And that's the way we can define formations control. So we modify actually the edge functions. Remember previously when we defined the edge function is defined based on the distance, But now what we could do, the edge functions is not only distance, we change it, it's just the inner angle. So the edge functions for every edge, it is defined by the inner angle. When we use the inner angle, we can use this as potential functions, and we use the same mechanisms. We use the gradient base and so on and so forth. And the theorem that we have come up here is that the resulting gradient-based control is able to guarantee local exponential attractivity of the desired shape. This is a bit of a simulation result. So you start from the wrong shape. If you look into the centroid of the circle, and circle is representing the shape of the robot. So we are no longer assuming that the robot is a point mass, but it is a circle. So it has a circular shape. So it started from a wrong shape, and it is able to converge to the right shape shown in the rectangular in an exponential way. So the right figures just showing the distance that is being realized, and the bottom part is the error, where you can see that the error converges very fast to 0. Now, the heterogeneous sensing case, I'm going to try to make it very fast. The problem now is we try to imagine now, I'm going to implement different type of sensors. Why do we want to implement different type of sensors? Because maybe one sensor is more expensive than the other one, so you try to do a mix of those. So one is very accurate, the other one is cheap, and you try to combine them. So can we achieve formations using different set of sensing mechanisms? The answer is partially. So we can combine it, but we have to be careful. So sometimes we have to be careful in the gain, for instance. Similar to the previous problem when I mentioned about the sensor bias or sensor noise, as has been asked by the audience, it can introduce undesirable motions when we are using different type of sensors. I refer to this paper, but it's already published, so it's no longer in archive, it's already published. And a simple problem I will show you in this plot. The left one is where we have a good case. So when I said about the good case, is that when the gain is tuned properly, they converge to the right one. What do I mean by the right one or the setup? We take a look into the setup on the top right. The top right is indicating how every robot is being set up. We consider 3 agents, for instance, where 2 agents are using the same sensor. So if it is red one, meaning it is measuring, it can only measure bearing, and the blue one means that it can only measure distance. So in this case, robot 1 can only measure distance, robot 2 and robot 3 can only measure bearing, or vice versa. Robot 1 can only measure bearing, robot 2 and robot 3 can measure distance. So with these 2 different cases, we can see on the bottom left, when we start from the initial conditions shown in the dashed line, so bottom triangle, when we set it up the gain of the gradient-based control, it can converge to the right one shown in the orange triangle. But when we are not setting up properly, then we can go to the wrong thing. So that is shown on the bottom right. So in the bottom right, when we start from this dashed line triangle, it converges to the wrong shape. And not only converges to the wrong shape, the shape is constantly moving to a certain direction. And that direction is dependent on the initial conditions. So this is kind of showing that you can imagine that you could implement different type of sensors, but please be careful. And it is still widely open. So the analysis is quite tricky, and how it is generalized to more than 3 agent case is slow. So you can try to investigate yourself or with us if you are interested in this problem. Now the last one, this is a kind of an excited one. When we look into the formations control I said earlier that everything is implemented in a distributed way. But imagine in the future or in the near future, when we have edge computer or Google Cloud, and we would like to implement everything in a Google Cloud. And why we implement everything in Google Cloud, maybe we would like to outsource all the computational power somewhere else. Now, in the current setup, everything is implemented locally. So everything is being put there. But if it is difficult to have computing unit there, we would like to see whether we can implementing it at the edge. Now, if we imagine the current technology to try to implementing controller at the edge, even though we think about the cybersecurity, what we can imagine is that every sensor's measurements, you encrypt the information, you send it to Google Cloud, but if you like to implement your controller, Google Cloud needs to know the key. So that means it has to be able to decrypt your data, it is able to retrieve your raw data, and then from the raw data, it computes the control log, and then it encrypts it again, send it back to you, and then you decrypt it, and then you implement the control log locally. We might say, yeah, in this case, it is secure because everything in the pipeline of the communications is secure, so it should be fine. But of course, we as a user, we do not want Google knows about our controller, or we do not want Google to know what is actually the dynamics of our agents. So if we are using a motor of Honda or motor of Toyota, we send all the measurements to Google Cloud. When they are able to decrypt the data and use the raw data, they might use system identifications. From the system identifications, they see some resonance and frequency response, and then they will be able to identify, this group is using a motor from Honda because of these characteristics in the measurement. So we do not want Google to know what is actually the machines that we are using. And the way we try to realize that is actually using homomorphic encryptions. And the way we do that is everything is being encrypted, and at the Google or in the edge computer, they just compute everything in the ciphered data. So they are not allowed to decrypt it, or they do not have the key to decrypt it in the first place. So what they can do is just, this one is becoming like a dummy terminal. They do multiplications, they do additions, but they do not know what is actually what they are computing, because those are just numbers. And after they're computing those numbers, they return back to the agents, and every agent, they decrypt it locally. When they decrypt it locally, they can use their own local key. So every agent can use different keys, and then when they send it to Google, even though they are using different keys, they do multiplications, additions, and then they return it back. They decrypt it using their own local key. And in fact, that works very fine. And you can take a look into the paper that we have that is accepted in the IEEE production letters and will be presented in Cancun for the CDC this year. So this is one of the example of the simulations. We try to make formations of 4 robots like before, 5 edges, and in this case the error goes to 0 as expected. Of course, because of the encryptions, then the average computational time for every time is increased quite significantly. When there's no encryptions, when everything is using local controller, it is the computation is very fast. But when you're using an encryption, because there's encryptions and decryptions, takes quite a long time, then the computational time increases by 4 in order of magnitude. But this has an increased, this increased cost is at the expense of having a better privacy and security of your data. Okay, so this is the last one. This is a work that is related to the source seeking problem that we discussed yesterday in the group meeting. We tried to see how can we have a source seeking. I hate this music. Anyway, So the problem here is that we try to locate a source, and we are using only local sensor here, and it is able to converge to the right source. Why this problem is of interesting, I will stop it. So it is of interest because that can be used for locating a dangerous substance, or if you are thinking about a fire situation, then you can try to locate where are the exit area. Or if you are thinking about the mining, then you are able to know where are the locations of the exhaust or the outside. If you are talking about the chemical substances, then we can trace where is the source of that chemical substance and so on. So the perspective, the development of distributed control for collaborative autonomous systems enable guaranteed performance of a team only based on the local measurements and local coordinate frame of reference. The real-time communications can then be used for higher level tasks. So we are not using communications for the sake of maintaining formation of motions. In this case, if you are talking about autonomous vehicle, the use of V2V or V2I can be used for high level tasks, and the low level task can just simply use the local sensor. So you are not really burdening the communications channel. So the high level task can be, for instance, for simultaneous localization mapping, or 3D real-time sensor networks for measurements and so on. So you can see this is one particular example. You see that there's a very large wind turbine blade is being transported, and we can do this transportation using many small robots just to transport this very huge infrastructure cables. So I would like to thank my colleague in my group, also PhD students and graduate students. Many of those work is done by our master students, and I would welcome as well the master students from instrumentation and control to do further work in this endeavor. And with that, I would like to return back to the moderator.
Please give big hands to Bayu. Yeah, I think it's very interesting. So, is there any question from anyone from online or offline? So I have questions about the trend of the autonomous vehicles. But what do you think about the combinations between? So you mentioned about the collaborative of autonomous vehicles, right? So how about the collaborative of autonomous vehicles with human driving or human control systems? It means that we need to consider about the intentions of other vehicles that driven by humans.
So I always like to think in the classical control sense. So I know that some people try to imagine using learning to try to solve those or try to learn the human behavior. But to me, whenever we go to a highway, the humans' actions are already restricted by the fact that they have a driving license. Since they have a driving license, the actions that they can do can be really limited. They are not going to create a crazy movement. So in that case, I'm answering this in the philosophical way. Right?
So, in Netherlands, maybe.
So in that case, then we can think on the way we formulate the problem, like using the this discrepancy, like before when we are dealing with the disturbances. Then the behavior of the human can be represented by some bias or by some theoretical motions, could be. And whenever we are dealing with autonomous agents, then that autonomous agents try to limit the possible motions by humans in a certain way. So then it is able to implement some estimator. And then when, for instance, when the problem in the Netherlands, we do have a bit of a challenge. Whenever I took my driving license, when we enter the highway, the highway there is actually 130 kilometers per hour. Everyone is driving 130 kilometers per hour, no matter what. And one of the difficult part in passing the driving license there is how can you enter a busy highway with a 130 kilometers. You should not stop. If you stop, then you fail the exam. So basically, you have to enter the highway, and you cannot shout. You cannot open the door to the other to the drivers that you are going to enter. So you have to use eyes to enter. So you could imagine that actually the behavior of the other agents can be represented by one of the formations agent
with bias.
or the other driver is actually implementing our formations control.
So there is a law enforcement in Netherlands whenever you don't achieve that 150 kilometers per hour, then the law enforcement will catch you.
No. Yeah, because if you drive too slow, then you are creating a traffic jam. So they're not going to enforce you and say you have to. You are driving too slow. They're not going to put a fine for that. Everyone tries to drive optimal. But the other driver, because they are performing similar to the formations control that I've shown here, when there are some agents try to enter, the response of the other agents is try to step away. And that's the way human is doing as well. So in that case, if we are dealing with autonomous agents with other robots, other car with human, we can abstract the other humans simply by autonomous agents that has implemented the formation. Maybe that's the way I try to imagine it.
Is there any relation with now in the Netherlands? Police use Porsche.
To use what?
Porsche car. Porsche. You know the high-speed car, Porsche?
Pursuit car.
Yeah, Porsche.
Porsche, yes.
Yeah. So it was several years ago. I showed you in the use of Porsche.
Yeah.
And is it related to like you have to drive 130 and then you drive faster than the police should have a very better car Porsche just to catch the.
Yeah.
Are they still using Porsche now?
Yeah, so they're using a high-speed car to catch someone who is actually driving more than 130.
But you don't need a Porsche for 130. You can
Innova.
No, but in Germany, of course, you know how Germans drive. They can drive up to 200 kilometers per hour. So their car
you
is
don't use Porsche. You use only BMW.
right.
So German driver.
It was amazing that the policemen used the Porsche, the autobahn. That's okay.
Yeah.
Are they still using this?
I have no idea. Geen idee in Dutch. Any more questions from online? Yes? You can turn on your microphone. I don't know who is going to ask. So, yes, right.
I would like to ask about the time constraints. If the formation is constrained by time,
So you were talking about the finite time.
yeah, the formation should be correct within a specific time. And what can be the possible solution?
Or you change the gain. So typically you can change the gain, or you can make it higher, because it's just exponential convergence that depends on the gain. But if you really wanted to realize a finite time convergence, then you have to change slightly the potential functions, where the potential functions becomes there's a weird L. So you see that the L is I put it 1, 2, 3, 4, 5 positive natural number. But when you would like to realize finite time, then you allow to use L which is less than 1. So when you use L less than 1, then the resulting control law contains a square root of something, and that enforces non-finite time convergence. But anyway, it's going to create a non-smooth behavior because it's finite time, and then after that it goes to 0. But in a numerical, it goes to a complex number in the equation. Because you cannot really have a solution that goes to 0 and then 0, because sometimes there should be some smoothness there. Anyway, you could try to do that. And does that answer the questions? Pak Anugrah, go ahead.
Oh, yeah, thank you. I will go back to the illustration when you describe the velocity calculation for each agent.
You mean this one?
I think in the beginning of your
Ah,
slides.
okay. Yeah, that's too long. Yeah, that's too long. And then?
At the beginning of your slide, and then I think if we see the graph that you perform at the beginning of your slides, and there is so you said that the edge represent which agent measured which agent. So I just want to confirm that is it correct that the velocity generation suppose that there are two agents that their distance is not suitable, so not correct, okay, and then who will be responsible to make motion?
Both. Yes.
Even that the agent that measure the others is only one agent.
That's why I mentioned earlier the arrow can be misleading. So I put the arrow just for the sake of a simplicity in writing down the incidence matrix, but the implementations, it is both ways. So it is an undirected graph, we call it. So there should not be an arrow there. It's just both agents are measuring each other, and both agents are implementing.
Yeah. I think that's the easier way, right?
Yes.
Yeah, I think the easier way. Okay.
That's
One more question is in the case of obstacle avoidance. So suppose that we have 4 agents performing rectangle with a specified distance between its agents. So when one agent detect obstacle, and then they will make the formation for a while, and after that they go back to the desired shape, right? So my question is that so we can say that when they form the formation, so that they broke their shape, right? So is it any like limitation how broke maybe how broke the formation should be?
I think it's there should be a trade-off. Either you are allowing a complete information exchange. If you are allowing complete information exchange, then what we propose is no longer useful, because you can just communicate everything to the other agents.
Okay.
But in our case, we are not allowing a complete information exchange. So they can only exchange about their collisions avoidance state informations. And in that case, it will introduce a bit like what you said earlier, deformed shape for short one. And how large the deformations, that's a design problem that I cannot answer at all.
Oh, really? Okay.
So we are not investigating in that particular.
So you didn't consider that issues, right?
Oh, no, not yet.
Okay, understand. Thank you.
If you are interested, I would be happy to.
Right, all right.
Any more questions? Yeah. Oh, there is a one in the back.
But if we wanted to use this formation control for transporting some items,
For what?
transport some items,
For transporting ideas.
how would we determine which agent we will use for the coordination of those agents?
Right. Okay. So the questions from the audience. If you like to deploy such a group of agents transporting an item from one area to another one, how can we determine which one should take the lead? In this case, since we are not considering leader-follower configurations, the one that is determining who takes the lead is actually a centralized controller. So we use the centralized controller to orchestrate how the group should move.
So this one of those agents will become
Yeah, just like I said earlier, when we are transporting this table, so we have a table. 4 of you try to lift each corner of the table. So you try to maintain your shape according to the distance of the edge of the table, right? And you're not shouting each other. You are too far away. Let's go. So it's a bit too noisy if you do that. So basically, just use your eyes. But then, when we try to bring the table to the other one, then you try to agree. Let's move to this direction. Then everyone goes to the direction. Of course, you can think another one that one is very strong and then is pulling, and the other one is just following. That could be, but we are not considering that solution. I hope you understand what I meant. So maybe there could be a solution by having an exchange of information about the forces. There are a lot of potentials. We have not explored those yet. You see, that's a lot of kind of open problem. So online. Okay, Hari Septanto. Pak Hari.
Yeah, thank you, Prof. Bayu. I'm happy to meet you again, even also in virtual. I joined your last lecture in apa bahasa Indonesianya, bahasa Inggrisnya stay ya, in School of Electrical Engineering and Informatics. Yeah, and in that last event, I asked you about unclear question actually about what about the Andrew Thiel's student talking in his dissertation, in his introduction in dissertation. And I now remember when I see this slide, yeah, about the potential function. If I'm not mistaken, the Andrew Thiel's student, he's talking about the singularity of the potential function. I see there is a singularity when cos theta k equal to half. What I want to ask you is it a significant problem in theoretical and also in practical aspect, Prof? Thank you.
Okay. So it's pretty noisy over here, but I think I would like to summarize your questions. Your questions is that this potential function is similar to the one that is proposed by Andy Thiel students. Is that what your comment?
Yes, bro. There is a.
It's similar, yes. And then your question.
My question is this singularity will impact to significant problem in theoretical.
Oh no, right.
Also,
right. So I think your question is because there is something on the denominator. In the denominator, it contains cosine theta k minus half. And then your question is whether singularity will be a problem there.
Yeah.
Okay, so I could confirm to you that in our theorem, they will not go to this singularity. So the theta k will always have a value higher than wait a second, it's higher. I think it's higher than half. So they will never go to this singularity point. And in particular, the singularity point is happening if I try to take a look into this example. That singularity point coincides with the fact that two circular agents here, they are really touching with each other. So when you touch each other, you can compute by trigonometry that the cosine is equal to half, if I'm not mistaken. So if your cosine is less than half, that means the robot is actually merging with each other. Is that true? Yes. Yes. So if they are very far away, so if the agent is very far away, then the inner angle is very small, and that value of cosine will be close to 1, right? Because the angle is very small. And when they are moving to each other, and then when they are touching, really touch with each other, that the value of cosine is becoming half. And because of the fact that I need to think, I think that the actions of the controller is becoming repulsions in that case. So I think that's the way we show it.
So it is locally, right? So it is already mentioned. It is only locally.
Yes.
Locally. Yeah.
Yeah, it's also locally, so we cannot start when they're inside with each other. I hope that answers your questions, Pahari.
Yeah, I think it is about the barrier.
The barrier of the infinity.
And also the angle, the field of view.
Yeah, of the field of view.
The field of view is less than 60 degrees. So when it comes to 60 degrees, it will repel. Yeah. In this case.
Yeah.
But it considers only one object, right? If you have more of this.
That K, one K is 1, 2, 1, 2, 3.
Yeah, but it's only detected only one object. No?
Yeah, here we assume omnidirectional. Because
it is omnidirectional.
Now, yeah, meaning all directions that you can, depending on the setup. So in this case, we can imagine that we are able to measure all.
But then it is an angle constraint.
Yeah, depending on how do we implement it. So we provide a theoretical analysis here that what would be conditions. And if we are talking about one relation with the other,
it is not about if it is go away from the 60 degrees, then the objects will leave you, will not cannot be seen by the robot. Is not the way.
No, so we are not really considering on what is actually the camera field of view. So we just assume that we have the information about the measurements of the angle. And of course, you can consider that, okay, I'm going to consider a very wide field of view.
Okay. So it is just the directions
to the outer side.
And then we just fixed it at the 60 degree.
When they are touching each other.
At the beginning, you were mentioning about the intelligence control, right? Your algorithms.
Yeah.
Which one is intelligence in your case? What intelligence means when other groups need related with quality.
So the classical control is not that intelligent, but
In the block diagram, you were mentioned about the intelligence. Right.
So if I try to address that philosophically as well, the way we talk about how evolutions happen is because of intelligent design. So similarly as well, then intelligence is a notion.
to neural network.
I don't want to. Okay, so I think it's already.
Yeah. It's the time. We are already 2 hours, and please give another big hand to Professor Bayu. Thank you for all the participants in online and offline. And if you want to contact Professor Bayu, you can contact through his email, I think, and then ask him if you're interested in the subject.
And I would like to thank the organizer as well, and I'm happy to open for collaborations. Okay. Thank you.
Thank you. There is a.
Yeah. Okay. So it's a bit of appreciation from the groups. Yeah, you can open.
Oh. Smart autonomous. So what is a smart autonomous?
You have to use it.
Oh, nice.
This is our jargon.
Smash.
Okay.
Okay. Great.
Thank you.
Thank you, Bayu.
Smash. It's not a boy band.
Shall we take
Picture together, yeah.